All right, so in this video, we're going to shift gears again. We're not going to talk about categorical data anymore. We're going to just shift to univariate or bivariate data. So we talked about the difference between univariate and bivariate. And in the beginning of the unit, when we focused on mean, median, mode, that was all univariate data. It's all one variable that we're measuring. In this lesson, we're going to now start to measure two variables and see what happens. So when we graph two variables, we'll get sometimes what are called associations or trends. So like, for example, if this was data plotted on an XY axis, we would call this a positive linear association. And that's because it trends in the shape of a line and it's going up, okay? This one would be considered more of a negative line or trending toward the line. We would call this one a nonlinear association. We might even call this a quadratic association because it's kind of shaping in the parabola. And then scatter plots that have no patterns, no trend, the data is super random, but it might look like this, where the points are all scattered all over the place and they don't have a trend or a pattern or anything like that. So we're going to start to look at graphs like this. Today we're just going to look at linear relationships. And so in linear relationships, sometimes we can model them with what's called the line of best fit. And so this is a estimated line that best models the data. So obviously we only use this with linear models. Okay, but we want to make sure when you do lines of best fit, you want it to be in the middle of most of your points. Sometimes there's outliers, but you want your line of best fit to model the most of the data. So we're going to talk about how to make one of those and everything like that. So let's look at this first example. The table below shows the number of prom tickets or formal tickets sold over a 10-day period. Plot these data points on the coordinate grid below. Use a consistent and appropriate scale. Draw a reasonable line of best fit and write its equation. So a lot of steps. So I kind of broke it up here. On my x-axis, I just counted by ones up to 10. And when you do this, when you're labeling, it's just good to point out, you should always just continue to label until the end. It's just good. It's more pleasing to the eye. And then I counted by tens, but I skipped one. So technically each box is worth 5. And so when I plot this, I'm just going to kind of estimate. So take a minute if you need to pause this video to do it, to label your axes, do that now. And now I'm just going to kind of plot my data. So 130, that's here. 235. 555. 760, oops, 760, and then 1070. Okay, so as you can see, it's not a ton of data points, but they do trend in the pattern of a line. So when I go to draw my line of best fit, the first thing you always want to do is you want to use a ruler, because that is probably the most important part here. And then when I go to draw it, I want it to get into the middle of most of my points. I want to try to get it first through most of my points. And if I can't get it through most of my points, I want to have an even amount of points on the top or as the bottom of the line. So I think that's about good when I draw it. And so I'll just kind of use my ruler here. And so it goes through one of my points, and then I have 2 points above and 2 points below. And so this is where the estimation piece will come into play. Our lines might be slightly different, obviously. So our answer for part B might be slightly different, but it should be close. Okay, so what kind of association does the scatter plot has? It has a positive because it's going up. Linear association. So that would maybe be how we describe it. If it was negative, we might say negative linear. If it was nonlinear, like it shaped it in a curve, I'd say nonlinear. If the points were scattered all over the place, I'd say no association at all. So kind of up here is where we talked about that's what you would use to kind of describe that part. The next says draw a reasonable line of best fit, which we did, and write its equation. This is the part where that's kind of review from the beginning of the year. If I'm writing a linear equation, it's in the form of y equals mx plus b, where m is my slope or my rate of change, and b is the y-intercept. So I'm looking at my graph right now. The best part about a graph is I can easily tell my y-intercept. So, although this graph isn't very helpful, this is my y-intercept, but it's really hard to tell what that exact number is. So I'm not going to use that. I'm going to have to calculate what that is. But what I do know is I know that I could pick out 2 points. I only need 2 points to find my slope of my line. So I'm going to start there. This point is right on my line, so I'm definitely going to use this one. And then I also see like this line goes right through that data or that grid right here. And so if you're writing an equation of a line of best fit, you want to use points that are actually on your line. You don't want to use points that are off your line. That doesn't make any sense. So I'm going to pull these points off and I'm going to make a table over here so I can tell what my slope is. So this is 445 and this is 1070. And so now what I'm going to do is find my change in y over change in x. From 45 to 70, I'm increasing by 25. And from 4 to 10, I'm increasing by 6. So I'm doing 25 divided by 6. And when I do that, I'm going to get a repeating decimal. So you could either reduce this, or I'm just going to write it as 4.16 repeating. And so that's my slope. Actually, I might leave it as a fraction because when I calculate. So I might leave it as 25 over 6 because when I go to calculate my y-intercept, that's going to be helpful. So right now I can write my equation of a line as y equals 25 over 6x plus b. And I can kind of tell my y-intercept is probably going to be about 27, but I can't know that for sure. So I'm going to have to use one of my points for x and y to figure out what that variable is. So I'm going to use, I don't know, 445. That sounds good. I'm going to plug 4 in for x and 45 in for y. And then I'm going to solve for what this b is. So 25 times 4 divided by 6 is going to be 50 over 3. So I'm going to kind of move up over here. So this will be 50 over 45 equals 50 over 3 plus b. And then I'm just going to subtract 50 over 3. And I'm going to make my calculator do that work. So I'm going to do 45 minus, in parentheses, I'm going to put 50 divided by 3. I get 28.3 repeating. $85 over 3 it's set as a fraction, or 28.3 repeating. So now my equation of the line is y equals 25 over 6x plus 85 over 3, or it might be, like if I change it to decimal form now, this makes sense. Either one of those will model that line of best fit, okay? And so this is helpful because say I want to know how many prom tickets I'll sell within 15 days. Well, that's not in my picture, but I can use my equation to plug in 15 for x to see what my output would be. So that's why line of best fits are helpful. They're helpful to predict things about data that we can't see. Okay, so yours might be different than mine. It might be close to mine, but because it's an estimate and we made our own line of best fit, that's why that will be different. So if you flip to the practice, that's all the notes. If you flip to the practice, you're going to do what we just did in this example. But then in this example, the line of best fit is already drawn for us, so our equations should be the exact same for that one. And then the rest of the practice is just practicing line of best fit. And then this has you predicting based off your line of best fit. So you're going to want to draw your line of best fit for number 5 and then use your equation to predict for the 5th year. okay? If you have questions, let me know.